we're going to start the part 3 of the tutorial. This will be focused on a small signal stability analysis of converter-based power systems. And so let's start for the contents. As said in the part 1, we're going to focus on two things mostly here: the grid modeling, so how we model the grid. And here I have two of them mostly use cases in academia, and also some indexes that we use normally as the short circuit ratio. And finally, I'm going to talk about small signal stability analysis methods, and we will compare passivity analysis and mix a small gain and phase. So let's start from where we stopped last time. So we have this feedback loop where we have the controller admittance and the impedance of the grid. And we need to know how to calculate or measure this impedance of the grid. And then also how to assess the small signal stability of the feedback interconnection. So let's start with the impedance of the grid, how we can calculate or measure this impedance. So we have the following grid where we have different converters integrated into the grid. We have also an infinite bus in this case, in case for guarantee that the power needed in any of the interior nodes are supplied, completely supplied. And basically, we want to go from this to a reduction of it. So in this case, we call this model a cron reduction, but also we can go from the full model to a short circuit ratio. So basically two nodes. And here we see the full system, and we basically transform the full system into another system with less nodes, only keeping the nodes in the frontier, let's put it like this, and eliminating the interior nodes. Meanwhile, in the short circuit ratio, we are looking for the grid from the perspective of any individual converter in the system. So essentially, they are different. One could be taken as totally decentralized approach like this. So we don't rely in anything more than our own information and maybe information of the neighborhood. Meanwhile, the cron reduction relies on having the full structure of the model of the grid. So the cron reduction actually keeps more information about the grid, meanwhile reducing the interior nodes, but is computationally heavy. In the other hand, the short circuit ratio keeps less information about the grid, but is a good index for knowing if the system will be stable. So if we compare the small signal stability with the short circuit ratio and it doesn't go through, we have a problem in the system, and we need to redo some controllers or to solve problems. And actually, as I said, is widely known in industry right now. But let's start with the cron reduction. So as I said, we have n nodes in the system, and active nodes that are the converters, and we're gonna choose one node to be the ground node. In this case, the infinite bus, and basically we want to compute what are the equivalent links between any entity, between every one of these nodes and their other converters in the grid. So we obtain something like this grid in here. Now I'm going to introduce something that will help us later. That is what is the AC line admittance. So we have basically R plus L circuit, and the admittance of it is the inverse of this matrix. Note that the matrix is not symmetric, so we have the minus E, and this is, yeah, I will say widely now. So we need to build the Laplacian of this matrix. The Laplacian is a matrix, a square matrix, where we have 2n by plus 2k, 2n, n being the number of converters in the grid, k being the interior nodes of the grid, and 2n because it is in DQ, in the DQ frame. So in this case, we have a complex matrix of 2n plus 2k, and basically we build the Laplacian matrix of this electrical network, and we can eliminate the interior nodes as this using the Cron reduction that is basically this equation. So basically we start from 2n plus 2k matrix, which is sparse in general, and we end up with a square matrix of 2n, which is generally way smaller than the first one. Also, note here something that we are dealing with admittances of the inside lines, and to convert it to the impedances, we need to invert the Q grid in here. Now, the short circuit ratio, there are a lot of indices to in these that could replace the short circuit ratio. Nonetheless, the short circuit ratio is the most used currently. So the short circuit ratio is defined as the ratio between the short circuit capacity that was something that Hamon presented in the morning session, and the nominal power of the device. So we have the short circuit ratio as a ratio that doesn't change at every frequency, but it is calculated at the nominal frequency. So this is an important thing, because instead of considering something that changes with every frequency, we consider something like the short circuit ratio as something that only that stays in the same value for all frequencies. This is not generally true, but helps us to analyze the system, and is something really, really easy to obtain. Nonetheless, there are several different indexes, as I already said. For example, the impedance merging ratio, which is, I will say, newly proposed, and you can find all the explanation in here. Also, the composite short circuit ratio that accounts for neighborhood inverters and so on. There is a weighted short circuit ratio and so on. So we have a plethora of new indexes, different ways to calculate them, and every one of those is more complicated than the other, but also gives more information than the other. So it's up to the engineer doing the stability studio to select what is the index that he wants to compute, and he wants to test or to represent the grid in this case. Also, we have the following situation where you know that you have a grid and you connect it to a node, but you don't know the grid. So actually, it happens a lot in distribution systems where even the DSO doesn't know properly the grid. And basically, you have to estimate what is the model of the grid where you are staying. or where you're connecting. So you start with something like the inverter filter, which is connected to the grid, and then how you can estimate this? There are several methods. I will explain one here, and is the injection of, so this is active of the identification of the grid, where you inject some signals, usually more than, like a bit more of the noise present in the grid. Then you measure the input and the output at the PCC, at the point of common coupling, and it will give you a representation, a model of the estimator of the grid. Depending on how you go, on how you calculate the model, it will be good or not that good, but it will give you a representation of where are you being connected. It is at least needed that you need that you inject two uncorrelated signals simultaneously and measure and remove the steady state, so you can actually calculate the impedance of the grid. In this recent paper in here, they calculated through predicted error methods, are also subspace methods. The most common one is RX, the ARX, that is implemented in MATLAB and works surprisingly well. So far, we have go through how we can represent the grid. So the grid is inherently really hard to represent, changes at every time, but we need to represent the grid in such way. So depending on how you want. So we can say that we're ready to check this. So we have our two blocks. And when we connect such blocks, we need to assess the small signal stability of such connection. So at the beginning, let's analyze the feedback between two operators, right? So in this case, we have H1 and H2, and the output and error equations can be written as this. So Y equal H1 times E, and the error in here equals U minus H2 times Y. So when we are rearrange the terms, we reach to the following equation, and here I wanted to have some explicit consideration, is that we need the feedback to be stable. And assuming that H1 and H2 are finite gain, so meaning that if you enter an input, it will be a finite output, the only thing that might happen is that this sum here, so the identity plus H1 times H2 goes to 0. So if this goes to 0, eventually the output can be infinite, and the feedback loop will be unstable. So we will focus on this. So we need, or we want to be sure that this expression here is never 0 for all frequencies. And here, the frequency domain methods, we start looking at them. So initially, the small signal stability methods needs that the converter impedance or admittance in this case includes everything: the controller, the passive components, and like everything that might affect the dynamics of the system. Also, as I said in the previous session, it will be linearized, right? So not only for, we need to prove for different linearization points of operation, and all of them should meet the conditions. And here, something interesting is that we can have such, we can use these frequency domain methods for stability in whatever reference frame you want it could be ABC, alpha, beta, DQ. It's usually used in DQ because it helps a bit with math inside, but it could be used in whatever you want. So we start with the impedance-based methods. So it was initially used for DC grids. It is good to quantify if it is a stable node, but it is quite difficult to know where the instability, if there is any instability, comes from. So you can know if it is a stable node, but not whether the instability comes. For the passivity, it is well established in the high frequency range, but in the low frequency ranges, we still have a lot of problems. Basically, it shares the same problems where we cannot detect where is the instability coming from. So let's start with passivity. In here we have two indexes. The first one is the input feed-forward passive index. So remember the age systems that I just showed. And so for every frequency, we will calculate the following index that is 1/2 of the minimum eigenvalue of the sum of the system evaluated at every frequency plus the system emission evaluated at the same frequency, and should be greater than 0. Also for the output feed-forward passive. But in this case, we will have the inverse of such system. And what it means is, here, the index of the passivity indexes doesn't have any physical insight. So this is quite important, and this is why we cannot relate it to physics and know what is going on. Nonetheless, we have the following passivity condition. So we already know that the input feed-forward passivity condition, which is this first one, and the second one, which is the output feed-forward passive condition. And the stability condition is quite easy to calculate. That is basically that input feed-forward of YC plus the output feed-forward of C grid should be greater than 0 for all frequencies. Or the opposite, the output feed-forward of YC and the input feed-forward of C grid. These have some conditions, such as the admittance should be minimum phase system. And so I will not enter into these limitations, but those are pretty well analyzed in this paper. This is fairly new, a couple of months ago. And something interesting that I can say in here is that if these the admittance of the converter doesn't have or doesn't meet the condition, doesn't mean that the feedback loop is not positive. What it means, what the condition is that the sum of them both should be greater than 0. So, meaning if this doesn't meet the condition, if it did have something that we can call an excess of passivity, the condition for the stability can be met. And so this is all in all passivity conditions. You have it have been under development for power grids in the couple of past years. And I will talk about now small gain and phase conditions. So in here, we have exactly the same feedback loop. And please remember from the analysis of the how feedback loop can be unstable, that this is the part that we are interested to see, right? So what we can see here is that if this H1, that is the multiplication between both systems, reach to a gain of -1, this will be 0, and as this is inverse, the gain the output will be infinite. So the small gain theorem says basically that the maximum gain of the admittance of the converter times the maximum gain that is represented by the maximum singular value of the impedance of the grid should be less than 1. If it is less than 1, basically we can say, okay, there is a ball centering the origin, and the maximum expansion of it will not touch -1. And in this case, we remain in the safe zone. So this is the small gain theorem. Now the small phase. The small phase is quite new. It has been developed in the last 5 years, and basically have somehow the same spirit. We want to bound, in this case, the angle from -1, from touching -1. So now we have more properties that need to be fulfilled in order to apply this theorem. And one is that the sectorial properties that I will explain in the following slide. But basically, the angle here, we need to fulfill these two, what it means, these two. So we have a maximum angle for YC and a minimum angle for YC. So the sum of these two should be less than pi, and the sum of these two should be greater than -pi. What it means that is that the sum of the minimum angles should not include -1, and the sum of the positive angles or the maximum angles should not include -1 as well. So in both directions. And now what it means, the sectorial property. So the angles are calculated in the following way. We have an operator called the numerical range. For every, so I will go back, for every frequency, we have an operator. At every frequency, we have an operator. For every operator, we can calculate the numerical range that is basically a set in the Gauss plane that is always convex, one of its characteristics. And from there, we can actually define a couple of angles, two angles that supports such set. In this case, we have three types of properties here. One is, this is sectorial, so it's completely, 0 is completely out of this, it's completely out of this set. This is quasi-sectorial, so 0 is in the boundary of this set, and also semi-sectorial, which is this. Some set which doesn't fulfill these characteristics is the following one. So 0 is in here in between. We have no possibility to measure the angles of this set, right? Now, how says the small gain and phase theorem? Basically, we need to meet one of the previous theorems, or either you meet the small gain theorem, or either you meet the small phase theorem. So in this case, you have the possibility of choosing one, or fulfill stability with one of those theorems. But keep in mind that in the case of the small phase theorem, both YC and C grid should meet the sectorial properties. So which is a bit tricky in some cases. So summary, or either we say, okay, the gain is not enough to touch -1, or the angles are not that high that doesn't touch -1, and therefore this gain will never be 0. And the gain of the system will never explode to infinite. And let's see one small example of this. In the following one, we have a grid following converter connected to a grid. The DC dynamics are neglected in this example, and we are connected through the grid to a LC filter, where basically we take measurements to our controller and put it back to the inverter. So this is the feedback loop that we are analyzing here. So we represent for facility 1, and also for the sake of being clear in here, we represent the grid as a short circuit ratio, right? And we have the following inverter admittance, and this exact model you can find it on equation 23 in this paper. So basically something that you can implement easily. And the linearization points are this. So this is full power. And we have here another linearization point where the voltage is the nominal voltage, but we have ID0 and IQ0 in different set points. The rest of the variables are kept the same. And here we have something quite interesting to see. So the small gain and phase, this is the comparison case 1. We see that from, this is around 3 hertz, below 3 hertz, we cannot certify the stability with the small gain theorem. So basically, when it crosses, the C-grid should be upwards. But we can certify the stability in this region with the small phase theorem. So these two regions, these regions are the maximum and minimum angle of YC. Nonetheless, here it touches pi and violates one of the conditions of the small phase theorem. And in this case, we cannot certify stability below 0.01 hertz. So extremely low frequency. Now, with the passivity indices, we have the input feed forward of YC in here and the output feed forward of the short circuit ratio in red. When we sum both of them, we see that the sum of both of them is positive always. But something that I want to recall that it was said in this presentation is that the admittance of a grid following converter is inherently not passive. So it relies also in passivity of the grid at some point for the low frequencies. So this was the case 1, where basically the passivity framework was able to certify stability in the whole range. But what happened if using the same converter, we just changed the linearization point? Now, the linearization point, we see something quite interesting in here. Is kind of the same plots for the small gain, so I will not go through them again. But in here, you see something that is interesting, and is that we cannot calculate the phase for the low ranges. So what's happening here is that the numerical range encloses 0. And when it encloses 0, we can actually not calculate it, and then we can use the small phase theorem in there. And what happened with the passivity index is the following. When we assume the both of them, so the red one and the blue one, the passivity index now is not certifying the stability of the feedback loop for frequencies below 0.05, if I'm not wrong, below. So even with the same converter, with the same controller, but different linearization points, we see that neither the stability analysis using mixed gain and phase and passivity analysis fulfill the full range of frequencies. So in this case, we are here with some of the top and more recently small signal stability analysis for power grids. Nonetheless, it doesn't mean it is not useful, but yeah, you should take care of it. Now, finally, some practice recommended if you want to analyze the stability of feedback loops using passivity or mixed small gain and phase. One is that consider the evaluation of the short circuit ratio or another metric, meaning that the grid could be represented in a good way initially, but one of those indexes. And if it doesn't meet this index, is something wrong. So there is something wrong that needs to be tackled and addressed immediately. You can validate the small gain, the small signal stability through different linearization points. And finally, you can perform large signal stability analysis. That is what Ali will talk in later. So finally, we start with this feedback loop. In the first session, when we analyze the admittance of the converter, and in the second session, we analyze the impedance of the grid, and we were able to assess the small signal stability of both the interconnection, the feedback interconnection of them both. And with this, I finish. Thank you so much for your attention.